All right, let's continue in our adventures of exponential relationships. So today we're going to look at geometric sequences. Sounds like a fancy shirt. Our objective is to write and use recursive formulas for geometric sequences. So we're going to have to kind of unpack what those two things we've been talking about. So geometric sequences. In a geometric sequence, the ratio of any term to its preceding term is a constant value. So it's a value that keeps kind of playing out all the way through, and it's a pattern that we can see. So we'll talk about that. So a geometric sequence with a starting value of a, so that's where we start, and a common ratio r is a sequence of this form. So I can say, like, there's my starting value, and my second value, the second term that's happening is my first value times that ratio. So for instance, like if something's being like doubled or something like that, I can say, well, if I start at 5, well, I got an example. Okay, so I can start at 5. Well, the next term in line is going to be 5 times 2. Okay, it's doubled. My next term in line is going to be 5, but it's going to be the 2. Excuse me. It's going to be the 2 squared. And then it's my starting point 5 again, times 2 to the third power, because I'm watching this thing build on. So that's called a geometric sequence has a common ratio, and we'll talk about kind of how do you find that. So we also have two other things. We have a recursive and explicit definition that plays out. Now, a recursive definition, that happens when you want to find like the next term. So you would use a recursive equation to find the next term in line. Okay, and an explicit definition, so an explicit pattern would be if I want to just run my formula to find out like the 100th term or the 50th term without having to write out the whole pattern. But this all comes down to a starting value and a common ratio, two things you need to interact with and find these things. And those are what make it, like it says, unique to a geometric sequence. So let's practice this out, because that was sure a whole lot of words and a whole lot of stuff. So let's see what happens when this is played out. Okay, so which of the following is a geometric sequence? Now the geometric sequence, remember, it plays out when I see a ratio happening. So I can look at 200 over 20, and that is 20. Oh no, that's times 10. So it's times 10 between these two. 2,000 over 200, and I can see that it's times 10. 20,000 over 2,000, so just looking at the next two terms, and I can see that it's times 10 and times 10. So I can see my common ratio is times 10. This indeed is a geometric sequence. When I look at B and I do the ratio of 4 over 2, I can see that it is going to be times 2. And if I do the ratio of 6 over 4, I can see that it's times 1.5. So that already tells me like this is not a geometric sequence because it's not a common ratio all the way through. Now look at C. Now this looks kind of strange, but let's see. Negative 5 over 5. That is going to be like a negative 1. Okay, let me look at this guy. 5 over negative 5. That ratio is negative 1. Negative 5 over 5 is negative 1. Negative 1. We do see that this indeed is a geometric sequence. Nice. And that would say, like for instance, this guy right here, we would say the common ratio, which we're using as r. The r value is negative 1. Actually, not the r value, that means something else. This is just we're using the variable r to represent our common ratio. This common ratio is 10. Why don't you go ahead and try it on these ones? All right, for A, I can see that my common ratio is 3, so r equals 3, so that is a geometric sequence. B is plus 3 each time. Okay, so that is not a geometric sequence, but it is an arithmetic sequence, like a linear relationship that's playing out here. For C, it is times 1/3, so my ratio is 1/3, so that is a geometric sequence. And D is just not. It's just a list of numbers. It's a list of numbers. Any geometric sequence can be written with both explicit and recursive formula. Explicit and recursive formulas. Okay, we'll talk about those. Okay, well, let's talk about it right now. The recursive formula is useful to find the next term. So recursive formula is good to know, like, what's the next one. Explicit, which sounds big, like explosive. It's just explicit. This formula is good for finding like anyone. The nth term is what we call it. So if I want to jump up and see like what's going on in the 100th term, I would use the explicit formula. So we're going to find the recursive and explicit formulas. Find the recursive and explicit formulas of this sequence. Okay, so a couple of important pieces we need for it is we need our starting point, which we called A in our formula. And then I also need to find my ratio that's playing out in each one of these. And when I build out my ratio, so I can see like 21 over 7. So 21 divided by 7 is 3. And I'm going to try 63 and over 21. And somebody in the classroom above me is dropping bowling balls, it sounds like. 63 over 21 is 3, so that I know my ratio is 3. So I know my R, and I know my A term. Okay, let's go ahead and play these formulas out a little bit. So I communicate by saying this. The first term for A is 7. So semicolon to kind of keep communicating. And now I'm looking for the nth term, the one I'm looking for, which is going to be the next one. So the next one I'm looking for, the nth term would be, I'm going to take, okay, now I'm going to write something in subscript, but it's just communicating. Okay, so n minus 1, so I'm going to take whatever term I'm interested in. So like for instance, 1, 2, 3, 4, 5. If I'm looking for the 5th term here, if I want the 5th term, okay, I need the term in front of it. So that's where this plays out. So it's my 5th term minus 1. So I'm going to need the 4th term in order to make that happen. And I'm going to take that and I'm going to multiply it by my ratio. So my formula for my recursive pattern that I'm playing out here is going to be whatever term I'm looking for, minus 1 times 3, because that is my ratio. That's what I'm looking for. This is my formula. It looks really algebra-isnator, but this is what's going on. So if I want the 5th term, I'm going to take the 5th term minus 1, and that's just telling me, well, what is that term? Well, the term is 189. So if I plug it in there, it's going to be 189 times 3. And that will get me, so again, I'm looking for the 5th term. That's what this is saying. I'm looking for the 5th term. I took the 5th term minus 1, so it's the 4th term, and that is 189. Multiply it by 3, and I should get my 5th term. And what is that? 189 times 3. It's 567. So that's my recursive pattern to be used when I'm looking for the next term, and I just need the one in front of it. Now let's talk about the explicit formula. It's still going to use my ratio. It's still going to use all the important pieces, but it looks a little bit different. So this is saying, so I'm looking for a certain term. Okay, that's what I'm looking for. And when I play this out, so I've got my initial term, okay, my starting value. I'm going to multiply that by the rate, okay, but I'm going to use it to the power. So this is where exponents play in here. N, okay, so that's, again, here's my N. It's the one I'm looking for. So it's N minus 1, which kind of plays it out here. So let's look at this whole thing. Again, we're going to look for the 5th term. So if I, you know what, let's just substitute things in that we know already. So I'm going to rewrite my equation. So a to the nth term equals, the first term is 7 times, I know my rate, so it's 3 n to the first. So what my equation right now here, and this is the answer, my equation is waiting for me to describe what term I want to use. Let's try it. So we're looking for the 5th term. Again, that's not an exponent. That's the word I'm looking for. It's not an exponent, it's just a subscript. It's just talking to me. Okay, my starting one, and it's 3, and I want the 5th term minus 1. And when I simplify this out, my 5th term is going to be 7 times 3 to the 4th power. So 7 times 3 to the 4th power, and I get 567. All right, I'm going to move this down a little bit. And here's a couple I want you to try. You're going to do both the recursive and explicit formula for each one of these. So go ahead and press pause and then take a look. So again, recursive and the explicit formula for both. And why don't you go ahead and then use your formula to find the 1, 2, 3, 4, to find that fifth term again, to find the fifth one in the pattern, just to try it out and see like, whoa, this really works. Pause. All right, there's a lot of math up here. Holy moly, you might need to pause it again and take a look at your work and then look at mine. I kind of expanded it out all over the place so we can see what's going on. So again, I did recursive first and then explicit, and then recursive first and then explicit, and I worked it out to find the fifth term out, and it worked for both. I was able to get the correct answer. Again, press pause and look it over. Yeah, it's kind of the best way to do that. Okay, using sequences. Okay, so now we're going to use it. So we saw it, now let's use it. Okay, so what is the price of the item after the sixth markdown? So 1, 2, 3, 4, 5, 6. So it's the sixth markdown. So it's going to happen right there. All right, for each one of these, I'm going to go ahead and use, I'm going to use the explicit formula because I want to know after the sixth. So really, it's the seventh one that I do want. So I'm looking for the seventh term. So I'm looking for the seventh term. And in explicit formula, which skips out a little bit, I've got my ratio. So there's my R. And my first term is 60. So my recursive formula tells me that I need to start with my initial amount, which is 60, times my rate, which is 0.85, to the n minus 1, so n being 7 minus 1. Right? Okay, so my seventh term is 60 times 0.85 to the sixth power. 0.85 to the sixth power is like 0.37714 times 60. And 7 out will be 2263. All right, this one's a little different because it's got a common difference, so it's going to play out a little bit, but we're still looking for the seventh term. So we still want to look out for the seventh term. So let's look at this. So the recursive pattern would tell me that I'm going to take the nth term, okay, and I'm going to take the nth term minus 1, like we've always been doing. But in this time, instead of multiplying, because that's a common ratio, this is a difference, so I'm going to subtract it. So from the previous number, I'm going to take away 8, and I should get my answer, which makes sense, and that should fit. Now, explicit formula, a little bit different, but we got to pay attention to that. So I'm going to be looking for the nth term on this one again, playing out on the nth term. Now this time, I'm going to, let's see, I've got my difference happening, and it happens at each level, so each day or each time it happens. So I'm going to be multiplying because I need to know how many 8s there are, and it's the day I'm looking for minus 1 because it's dependent on the number before, and I need to include the starting point. So I'm starting at 60. So for this one, I would use the explicit formula because I'm going to go out to the seventh term. So I can go the seventh term out. It's going to be -8, and this is the seventh term minus 1, so 6 plus 60. End up with the seventh term out to be $12 as it keeps discounting. All right, once you go ahead and do this, so press pause and you play this out, you can see that it's probably good to write the recursive and explicit formula for both, and then probably just use the explicit formula to find the 8th term. Press pause and give it a try. All right, so to catch all these, you might need to pause this. You can take a look at your work, but again, I built both the equations out so I could use them, but I ended up using explicit because I wanted to jump up to the 8th term. Now you can also represent a sequence by using function notation. This allows you to plot the sequence using the points n and n to the 8th, where n is the term number, okay? So here's your equation, where n is the term number we're looking for, and an is the actual term. So let's unpack what the heck that's talking about. So writing a geometric sequence as a function, and we can graph functions. A geometric sequence has an initial value of 6, okay? So that's good. You need to know that. So initial value, so a to the first is 6. Common ratio of 2, so r equals 2. Write a function to represent the sequence, and then graph it. And I can do that here. So a to the nth term, so we're trying to find the nth term. My first term is 6 times my ratio, which is 2, and it's n minus 1. So now I can build a t-chart. I could do some substitution here. So let's do this. We're going to do like a function of 2. So that's basically saying where n is going to be 2. So it's 6 times 2 to the 2 minus 1 power. And for that, I end up with 12. I can try with a function of 3. And that's going to be my initial. It's 3 minus 1. And so 2 to the second power times 6, I end up with 24. And I do a function of 4. I'm basically getting a t-chart going here. I'm going to plot some points here. So that is 4 minus 1. I simplify that out and I end up with 48. And my 3 points kind of get me going, but because this is going to curve, I'm going to get one more point on here. So function of x, or function of 4. So I'm going to do, it's my initial value times my rate, 4 minus 1. And I'm going to get 96 on this one. And so the points I have, the points that I can plot on my t-chart, x and y, is going to be at 2, 12, 3, 24, 4, 48, and whoa, I'm missing a number. 4, 6, 2, whoa, what's 2, 3, 4, 96? Oh, this is a 5. Okay, this is silly. Okay, that's supposed to be a 5. I'm like, what? Something doesn't match up. So that's 4, and that's for my 5th one. So my function is 5, and it's 5 minus 1 is my 96. That's true. Okay, and this is going to be the graph of that. That's what that looks like. So it curves nice. Exponential growth is what's happening here. Things are growing really quickly. Okay, I'm going to press pause and have you try this one. So why don't you press pause too? Race ya, ready, go. All right, this is the equation I used. I substituted in for 4 different points just to see what's happened. I built my t-chart. Now I can plot these. I had to change my my interval of my y value to 2 so I can fit some different points on here. And so I can see that my graph is going like this. Exponential growth. So that's what yours should look like as well. All right, holy Moses, that was a long video. All right, we should celebrate. Let's go and eat a jar of dill pickles using only our feet.